Okay, so let me start the introduction to OpenGL lecture. The OpenGL, you probably have heard that OpenGL is somewhere such as a smartphone or some gaming or virtual reality solutions. Now let me explain where the OpenGL comes from. So its origin is the Iris GL. GL is a graphics library. So GL, so it's a shorthand, is a GL. Then what is Iris GL? So it is a graphics workstation made by the Silicon Graphics Incorporated. So Silicon Graphics Incorporated is a company that made hardware accelerated rendering workstation and also operating system and also graphics library. So its library is called Iris GL. So they made some really great hardware, and they also implemented the pipeline approach in their hardware. So they needed some supporting graphics library that is Iris GL. Then from the Iris GL, so we may know its successor is OpenGL. Yeah, that's right. The OpenGL is a Open Graphics Library or OpenGL. The open means here the open to the Iris GL. So Silicon Graphics decided to open their API to the public domain. So the API is open, but unlike the modern definition of open software, the open software typically means open source, but in this case, this is not open source. It's a completely closed source library. Of course, there's an open source version in the Linux community, which is called Mesa. But usually, OpenGL made by the vendor of the graphics cards is not open sourced. But the only thing we can use open is we can use it. So that is the meaning of the open. So 1992, the Silicon Graphics opened the Iris GL to the public domain and renamed it to OpenGL. So we are still using the OpenGL. The OpenGL is basically rendering API. Rendering, so we don't have an idea yet, but simply let me explain. The rendering is making something encoded in the computer, the visible in the display. That is a rendering. So in rendering, we simulate some physics, including light source, and some materials and objects and further principles in physics. So that is called rendering. The OpenGL is basically rendering an API. The API you probably know. The API is Application Programming Interface. Here, the interface is what is an interface? The library interfacing the graphics hardware and your programming. So that's why it is called API. So now we know that OpenGL is a rendering API. And so here we again see platform independent rendering API. Here, platform means more like the operating system. So Linux, so Windows and Apple and something more. So whatever we use some platform, the API stays the same. But that is the meaning of the platform independent rendering API. Then it is close enough to the hardware and driver to get excellent performance. So close enough to the hardware, that means the control from the operating system is minimal. The operating system cannot control everything from the rendering APIs such as OpenGL. And a lot of things are just directly to communicate with the hardware. So that's why we get excellent performance using the OpenGL API and also some graphics hardware. So I said, so it's a platform independent, but we often need platform specific or platform dependent features. That's how we extend it. So there's some extension mechanism. So that is so basically there's some core or some standards which is called ARB, Architecture Review Board, which is almost standard. So other than such a standard, we still can provide some extensions. So in practice, many different vendors want to provide their own quite super excellent features, but that is only available through the platform-specific extensions. For example, SGI or NVIDIA provided their own API. Also, the AMD and some ARM is a vendor for the mobile graphics processor. They also provided their own features through the extension mechanism of the OpenGL. So later then, the feature is the very common. Everybody uses that feature. Then that some standard community, which is called ARB, try to decide that this can be adopted as a standard or core feature of the OpenGL. Then, when there are some standard features, then they revise the version of the OpenGL to a higher version. That is the some system for improving OpenGL version. Still, it is an industry standard for 3D graphics, but it is an industry standard. So there are competing API. Typically, it's a DirectX. DirectX is a similar API made by Microsoft for their PC game and also their console like Xbox. The functionality, it was quite different around the early 2000s, but nowadays the functionality is basically almost the same because we use the same hardware and hardware vendors try to provide as many as features that they can do that in the manufacturing, and such their own or new features are available both in the OpenGL and DirectX. So, but OpenGL is its age is around more than 40 years, so it is quite old. So people also try to develop a new successor of OpenGL that is called the Vulkan. So Vulkan is another industry standard, and when we start to develop a new graphics application, then it is better to use a Vacuum instead of OpenGL. OpenGL is it's a complex and it's the older age, but if you really want to control everything for your graphics application, then it is better to use a Vacuum. But the problem here is a Vacuum is a very complex and difficult. It is not a very kind API for beginners. The beginners have significant problems in using Vacuum, so usually very skilled, experienced developers use a Vacuum, which is typically common in the some game engine industry, so like some low-level smartphone and or Unreal or Unity developers use a Vacuum, but usually casual programmers doesn't use a Vacuum for their application because that is way too difficult. So you are very good in understanding OpenGL and DirectX, then you can start a Vacuum. So OpenGL is still one of the best starting point for your 3D graphics application. And here's a OpenGL Management Consortium. So the name is called the Kronos Group. Kronos Group. So there's a website, kronos.org. So originally means early stage around the late 90s or early 2000. The OpenGL was controlled by the Architectural Review Board. So that is ARB. So that is a small community that can decide in which direction we go with OpenGL. So the members was SGI. Definitely SGI was a core member. And Microsoft, NVIDIA, and Hewlett Packard, and Apple, and 3D Labs, and IBM. Yeah, very, very famous companies that were involved in the ARB. So at that time, OpenGL was almost the only API that they need to control. But later then, there came much more the APIs for us with a similar inspiration for OpenGL, and they expanded to a different consortium that is a Kronos Group. So there are several levels of the members, and promoter members is basically the same as the previous ARB. So they have some right for the board of directors. So they decide the very important things with OpenGL and its related some APIs. So current members includes AMD. Yeah, you know that AMD makes CPU as well as GPUs. So they are interested in developing CPU specific something and also GPU specific something. So they are one of the key members. And yeah, definitely Apple and ARM and Epic Games. Epic Games is the company that makes Unreal Engine. You probably have heard that, one of the most famous game engines. And Google, yeah, everybody knows. And Huawei and IKEA. IKEA is the company for the furniture. So they are also quite interested in 3D visualization. So that's why they are here. And Imagination is one of the companies that made some GPU, usually for mobile processors. The Intel, the mainstream business is making CPU, but they also make a GPU. it's a quite long time since they may try to make some built-in GPUs. And NVIDIA, yeah, definitely everybody knows that is the most influential companies in the GPUs world and also graphics community. And Qualcomm also makes the AP for the mobile processors, and they also the member of the promoter. And Samsung, yeah, definitely Samsung has a quite big impact on the smartphone industry, so they are also a member of the promoters. And Sony, yeah, everybody knows, and Valve, which is the company for Steam, the game distribution platform. And where is Silicon? Actually, I have no idea what the company is. So they are the current promote members, and here's more on the active standards. This is at present there are the 20 standards, including OpenGL. Here, OpenGL is definitely the most important API of the Kronos, and it's embedded system version, which is for smartphone or embedded systems. And let's see, actually I don't know what it means. OpenVG is the Open Vector Graphics. And another famous one is a WebGL. So it isn't ports of the OpenGL ES to web browser. So your web browser, modern web browsers support OpenGL is running. So you can make your application so is running into a web browser. And EGL is the name is quite weird. So we have no idea what EGL means, but the naming is a bit misleading. But that is an API for the platform-dependent connection between OpenGL and platform in programming. That is the name of the the meaning of the EGL. And yeah, there are a lot of new APIs, but I have no idea. And Collada is some communication format for 3D asset exchange. So the asset exchange, that means that is written in the exchangeable format, which is XML. The XML is a pretty complex spec to specify something. So OpenGL recently made a new extension or the alternative representation of the 3D assets, that is a GLTF. TF is a transmission format, but that is a much lightweight asset change format, which is written in JSON. JSON is a JavaScript object notation format. HGX, I don't know. And OpenCL is a CL here is a computing library or computing language. So that is originally made by Apple. So Apple made a new API for general purpose GPU computing. Its name is OpenCL, which is affected by the NVIDIA's CUDA API. But CUDA is a platform-dependent API that only works in the NVIDIA GPU, but OpenCL works in any GPUs. And also it supports heterogeneous GPU computing, which includes the CPU as well as CPU. And VFXR, yeah, probably related to the virtual reality and augmented reality. Spur is another, what is that? It's an intermediate format for trading language compilation. So by default, so we need to write GPU-specific language, which is called the trading language. Then we compile the trading language, then that is compiled to the binary representation, which can be loaded in the GPU, but that is a bit inconvenient when we write in many different APIs. So we need some platform independent format to support some inter or cross comparison between the different graphics APIs. So Spur is like some intermediate representation for such compilation. And Vulkan, so as I say, Vulkan is a next generation successor of OpenGL, and it is has a significant degrees of freedom to control everything in the graphics application. So we know everything, then yeah, it is very good for the high performance applications. But you are beginners, then yeah, there's a significant problem. So even you cannot make a simplest some application with just a red color window. Making such a window is a very, very, very difficult. So that is a Vulkan. So for me, it took more than 3 weeks to implement it. Just simpler window and it's a color. Oh yeah. But you're done with OpenGL, then yeah, you're now ready to start Vulkan. Let's see. Yeah, I don't know. And next is old style OpenGL. The old style, you see old style, that means that there's a new or modern style. So in this course, I'm going to cover modern style only. So then we have to know what is old style OpenGL. So OpenGL, the current version is 4.6 or 4.7. But through OpenGL version 2.5, more strictly up to version 3.1. That means from version 3.2, then modern style OpenGL begins. So up to 3.1, the OpenGL was the old style. That was relatively stable, and also very important thing is backwards compatible. So OpenGL 1.0, the program still works in OpenGL 3.1 or 2.5. Actually it still works, but they are no more maintained. So the main feature is the features of OpenGL were fixed and nearly impossible to modify. So that is hard-coded in hardware, so there's no way to control. So as we want to program, but that was not possible. So such hardware pipeline is called fixed pipeline. So fixed pipeline was old style OpenGL, and API was optimized for such so fixed pipeline OpenGL. So fixed pipeline simulates the basic transformation and projection in vertex shader, and also Boolean function shading in fragment shader. So they do standard transformation and projection, but yeah, we don't have freedom to change how the objects are transformed. And also the shading is fixed in shader. So the standard was a Boolean function shading. That means nowadays we can change the content of vertex shader and fragment shader as we want. So now many of the architecture are deprecated in modern-style OpenGL. So such old-style OpenGL features are deprecated. Deprecated means we may use it, but that is no more maintained, and at some point that features will be removed in the future release. So that is not strongly not recommended to use older style OpenGL. More importantly, so industry now uses a modern style OpenGL only, so older style OpenGL is no more used in industry. That is still survives, but usually in only graphics courses. But in this course, I don't use older style OpenGL, and also you are not allowed to use older style OpenGL. You only have to use modern style OpenGL. And here's a brief introduction to graphics hardware. You probably heard that GPU is a graphics processing unit, which is similar to central processing unit, CPU. This is a dedicated unit for only graphics processing. So it was a graphics oriented processing unit. But nowadays, CPU is no more graphics processing unit. It is a more general purpose computing unit. So typical example includes the acceleration of the deep learning. The deep learning depends on the power of the parallel processing power of the GPU. So in graphics card, the number of cores around 3,000 in the NVIDIA's state-of-the-art platforms such as GTX 1080, 2080, or 3080. Yeah. So below you see the diagram for the systems. Where is it? Here, CPU and external memory, which is disk, and main memory, RAM. This is the typical architecture of computer, and we have one more subsystem. So graphics subsystem is also part of the modern computers. That we have special processing unit, GPU, and its own memory. So graphics memory and some of the reserved memory area in the graphics memory is called the frame buffer. Frame buffer is connected to display. In high-end graphics cards, it has a special graphics memory, but in low-end GPU, they usually share the memory with the main memory. But the memory is virtualized, so you don't see the what the memory is from main memory or other separate memory. You have you don't see how that memory is organized. So in your point of view, you always see the separate memory for the graphics processing. Here's an example of the NVIDIA GTX 1080 that it has 2560 CUDA cores. CUDA core is just simply processing cores. Their clock is 1.6 gigahertz. And they have 160 texture units and 8 gigabytes memory. And here's a brief architecture of this GPU. So I said brief, but yeah, seems to be really complex. Yeah, actually complex. So modern GPU is much more complex than the CPU's architecture. So there are some hierarchies of the core group. So this is the most smallest group.
here, this is SM. I think SM is a streaming multiprocessor group. So inside SM, then each in SM has 4 groups like this way, and here this green one is core, and here this is load and store unit and special function unit, which is like some mathematical functions here. And here's instruction buffer and work scheduler. This is a group of threads, and dispatch unit and register and texture cache. And also that texture cache is shared with L1 cache. This is texture unit and something like that. So it's difficult to understand precisely this architecture, and this is far beyond in this course. But you understand a lot of cores, and the architecture is quite complex. So a lot of core means the main advantage of GPU is a parallel processing power. And to use such GPU's processing power, then you need dedicated API that is OpenGL. Then, now back to modern style OpenGL. The modern style OpenGL is informally we can define like OpenGL since version 3.2. That is a modern style OpenGL. So that is optimized for the more powerful GPUs. So we intensively using GPU rather than CPU for higher performance. So CPU's job is pretty simple. They just trigger the GPU works for some previously defined commands. The application job is only send data and later then trigger the GPU program. Then GPU does all the rendering jobs as well as some computing. So that is for the GPU, general purpose GPU computing. So in this course, I'm going to focus only on modern style OpenGL. Basically, old style OpenGL stuff are not allowed here. So many of them are available on the web. So you may search up the web, then you can easily find old style OpenGL code. So that is useless in this course. So even I will not let you know what the old style was, so to avoid confusion. So basically, you have no idea what the old style code is. So that is important. So old style code is found in your assignment, then that basically means cheating. So you're cheating from the web source. So if you don't know exactly what the modern style or old style OpenGL means, then don't use the web code for your assignments. So the samples I distribute in this course is only allowed for your assignments. Another important characteristics of modern style OpenGL, so we are using user programmable pipeline. So I told you in the older style OpenGL, the older pipeline was fixed and there's a limited freedom to change the program. But in modern style, we can program, not really everything, but we have much more freedom to change how the GPU works for our drawing or computing. So basically, we can change the 2 parts in the pipeline: vertex shader or vertex processing, or fragment shader and fragment processing. So this is possible by GPU programs. GPU programs they are called shaders. So far, I didn't explain what a shader means, but shader is simply GPU programs. Later then, in shading lecture, that you're going to understand why we say it is a shader instead of the program or like a software, something like that. So preview is simply the vertex and fragment processor does shading. That is their main role. So for the moment, forget about why we say shaders, and shader is just a GPU program. So next is a modern style OpenGL is a totally shader based. So no default shaders are available. So you have to define your own shaders to use GPU. So default shaders had been available in the fixed pipeline. So basically standard transformation and the blend form shading was available in the fixed pipeline, but they are no more available. So we have to define, also we have to write our own shaders too, so that the vertex and fragment shaders work. So you should write vertex and fragment shader. And next is most 2.5 or previous functions are deprecated. Not all of them, but most of them are deprecated. So if you use the deprecate function, then nothing happens. Okay. Then here's a hierarchy by the OpenGL hardware generation and also its API. So starting from OpenGL 1.x, so they had focused on the fixed functions. We have limited freedom to change the parameters. And next is vertex and fragment shaders. Actually, they are available in 2.x, but they are not really consistent with the other part of the OpenGL. So they mix the fixed function and vertex and fragment shaders. That was in up to 2.x. So at that time, the main goal was surface realism. So we are focusing on how the color can be changed with our program. That was the main focus of the OpenGL version 2.x. From 3.x, then new shaders came, geometry shaders, and in 4.x, tessellation shaders and compute shaders. So in that case, they have more control over the shape. So here's a simple classification says shape realism for 3.x, 4.x. Actually, in this course, I'm not teaching geometry shader, tessellation shader, compute shaders. So they are quite advanced. So you learn vertex and fragment shader in OpenGL 3.x. That is the main focus. So you implement OpenGL, theory lecture from the other part of this course. So that is implemented in the using OpenGL API. So still there's no 5.x. So I think there would not be 5.x because this API now still changing to or evolving to Vulkan. Vulkan is the next generation OpenGL. So more advanced functionality is now available only from the Vulkan or DirectX 12. Okay, that's it for the introduction to OpenGL. So, introduction to OpenGL API. First, what is API? API is a application programming interface. That is API. So more precisely, it is a protocol intended to be used as an interface by software and hardware components to communicate with each other. So software, low-level software or the low-level hardware, it is very difficult to communicate with them in some native way. So we need some software to ease the communication. That is an API. Also, it is a library that may include the specification for routines, data structures, object classes, and variables. So simply, you can think that API is a sort of library. Examples include POSIX. POSIX is a API for Unix-like programming. So Unix or Linux-like environment. So uses this POSIX API, then the interface is unified and standardized in many different operating systems and also many different developing environments. Another example is a Microsoft Windows API. So to manipulate many things, some platform dependent things, then we need API to control many low-level stuff. So that is provided by the Windows API. So that is only for Windows programming. And also C++ standard template library, STL, that is also famous example, and that is also sort of API. So OpenGL is also API. Your graphics cards can do a lot of things, but you cannot control directly. So we need some library that is OpenGL. So it allows us to interact with graphics hardware and other software platforms via abstract forms of function calls. So we can communicate in high level without knowing the real details of hardware and also underlying some driver implementation. So we only focus on the logic instead of the low-level hardware. So OpenGL is a cross-language, also cross-platform API. So languages C and C++, Java, C#, Fortran 90, Perl, Python, Delphi, Ada, and almost most of the languages now supports OpenGL. But actually, such support is just wrapping for the C API. So in essence, the OpenGL API is provided only in C. All the other languages make their own wrapper library that is their own API, and in the end, actually they call C functions in the low level. So most efficient way of using OpenGL is using C or C++. So in this class, we're going to use C++. So platforms are Windows, Linux, Apple, which are the three major platforms, and other platforms also supports OpenGL. So cross-platform means platform-dependent things are not supported by OpenGL. Such an example is a windowing support. So windowing supports making window and getting some event from the operating system is definitely platform dependent. Such platform dependent things are excluded, and that makes OpenGL is pretty easily extendable to many different platforms, because we can just provide the platform dependent things in addition to the core of OpenGL. So windowing support is not included in the core of OpenGL, but many people are trying to make the platform-dependent things, but their API is still typically platform-independent. So we need a third-party library to support the windowing. Such an example is the most famous one is GLUT or GLUT. OpenGL Utility Toolkit. That is a GLUT. So GLUT was developed in the back in the day around 2000. It's pretty out of date nowadays. Even it doesn't support the 64-bit architecture. But the author is still working for NVIDIA, but he's no more interested in improving GLUT. So some of the guys made its own descendants, that is a free GLUT, which is an open source implementation of GLUT. So it is better than GLUT, but still lack of some modern features. So another library support like a GLFW. The GLFW supports most of the GLUT features and also additional features we need in the nowadays computing. So in this course, we're gonna use GLFW as a windowing support and also context creation. So to use OpenGL in your system, we need context, which abstracts some object that can communicate with the hardware and your operating system and also your application. So below you see a high-level overview. So you write application programming and drivers, and these drivers are so per device drivers exist in your system. So your keyboard, mouse, and display, and also your graphics cards has their own drivers, and we cannot communicate directly. So that is usually, in theory it's possible. It's very difficult. You can handle some hardware dependent things. So that is not necessary. We want to focus on the logical things. That is provided by this API graphics library. So OpenGL. Next is the OpenGL API. Lack of object orientation. It is a pure C API. So it doesn't support C++. There are some wrapper library, but basically that is on the wrapping for this pure C API. The official API or header file is only supports C. But of course, we can compile it in the C++. So due to lack of object orientation and also C++ features, then there are some shortcomings, such as overloading. So there are multiple functions for a given logical function. So suppose that we need GL uniform. So this function actually sets a uniform variable. Uniform is a global read-only variable visible to all of the pixels in your shader. So for the moment, you don't have to understand what GL uniform means. Just suppose that GL uniform exists. So its argument should have different number of arguments and also different types. So that's easy in C++. So we can use function overloading, but here that's not exist in C. So we append many suffixes here. So 3f means 3 floating points are the argument to this GL uniform function. 2i is we use a 2 integer. 3d is 3 double, and v is a suffix for pointer. So we provide just double pointer, but its content is like a 3 double precision floating point numbers are provided as an argument to this function GL uniform. The underlying storage mode is the same. So basically, OpenGL doesn't support where for the 1 byte or 2 byte types. So basically, we use a 4 byte types. So int, float, and unsigned int is a typical choice for OpenGL. So that's why underlying storage mode is the same. So we use just 4 byte. That is a default. So also the Boolean is supported, but yeah, that's just exception. So basically we use a 4 byte. So it is a C API, so we can easily create overloaded functions in C++. But an issue is efficiency. So always we have to 2 function codes to call a single C function. But this efficiency issue is not really important, but the more serious problem is there's no standardized way of creating C++ wrapper. So it is good to use directly C functions. Always it doesn't change anymore. So using C function directly is a good choice. So however, in practice, many of third-party libraries use OpenGL API with their C++ APIs. So that is for C. Why they made OpenGL in C? Because C++ came in 1984, but OpenGL came in 1981. So OpenGL came earlier than C++. That's why their choice was C. So this choice is natural in that age, but yeah, okay. Then next is OpenGL is a state machine. State machine, since it doesn't use OOP, many of the API states are stored internally. Many of the API states means OpenGL needs many global variables to control many things. Then such variables work as a state machine, and they are stored like internally. Internally means typically within the driver of OpenGL. For example, so you want to use depth tests. Why? you want to use depth test, then first we need to enable depth test. Then we have to maintain its flag in somewhere. So we may do that outside of OpenGL library, but that is inconvenient or sometimes inconsistent. You maintain many different applications. So it is safe and also easier to maintain inside the OpenGL API. So that's the implication of the state machine. So reading such states is not directly supported. So you never get the pointer to the internal state because that is completely abstracted inside the OpenGL API. So whenever you need to access it, then you have to use the query functions. So something like this. So GL get something. So GL get like an integer v, something like that. Then you get the pointer, so which is a temporary variable. Then the state is written to your temporary variable. Then you can access the state like a GL get integer v, and you provide arguments like a GL depth test. Then you can know depth test is now enabled or not. Function format. So function style uses a lower camel case style. That's a camel is here, so like this way. So this is a capital letter and this is a lower case. So here GL uniform 3F. So GL is a prefix, so it belongs to OpenGL library. The uniform is the function's name. Then starts with the capital letter here. And 3 is the number of arguments here. And F indicates the type to the arguments here. So X, Y, Z. So we have 3. So this 3 is from here. And their type is a floating point. And this is a typical naming of OpenGL functions. And as I already said, the V is often used, and V indicates the argument is a pointer type. So here P is a pointer to an array of type of floating point. But you have to make sure this P is a pointer to the 3 floating point array. Okay, that's a really high-level overview. Then next is a prerequisite, so how to use third-party libraries. Nowadays, open source software is common, so you can find many of the softwares are available as open source. In that case, you have to compile on your own. So that is very typical, but often you don't want, or other people don't want to expose the internal implementation. Only just want to provide binary files and so that they are linked and used in other users' applications. So in that case, such library is distributed like a pre-compiled binaries. So that is a common also. So there are standardized format for such distributions. So most of the binary distribution of third-party libraries are structured like this. So header file, library file, DLL file. The header file is just simply header file, and library file or in Linux, its extension is A, or DLL file is a dynamic linking library. So this is also SO in Linux, shared object. Header file contains the function prototype, and library file is, there are two types of explicit dynamic linking and implicit dynamic linking. The static compile or dynamic compile. In static compile, the binary is included in this lib file, but here we use a dynamic distribution, so lib is just empty. That is only used for the linking. And DLL actually contains real compiled functions inside it. But without lib, that is not possible in your compilation of your source code. So that is necessary only for the compilation. So what is DLL? DLL is a dynamic linking library. Dynamic means it is linked in the runtime. So using linking in lib at the compile time is just for the compilation is a made success. But actual linking is done in the runtime. That is a dynamic linking library or shared object. So in that way, pre-compiled binary objects that can be used for other programs. So below we see an example of the GLFW. So header file is include and glfw3.h. 3 is a version 3. And lib glfw3dll.lib. So this DLL file is for this lib file is for linking for DLL distribution. If we use a static compilation which contains all the binary inside the lib file, in such a case we use a different naming such as glfw3s or just lib. So we use DLL, so we use glfw3dll.lib. And bin directory, we have to locate the glfw3.dll. So this DLL is not related to the compilation. So even though you don't have this DLL file, still your compilation doesn't fail. But when you're running your application that without this DLL, then your program could complain, so it cannot find this DLL file. Okay, then now you understand the structure for the DLL distribution.
Next is installation. So first I assume the platform as the Windows and Visual Studio. So you first have to download and install Visual Studio, typically Community Edition. The Community Edition is freely available for college students and also personal developers. So that is a fully functional as a professional version does. So don't download the illegal version and always try to use a legal version of the software.
So installation here is a local copy. So there are two ways, global installation and local installation. Global installation is you place your DLL files to your system directory, such as system32 in Windows directory. That is okay while you are developing your program, but later then you may use different machines. In that case, your DLL is gone. Then your program is running and not running anymore. So keeping all the necessary things in your local project directory is recommended here. So the reason, again, that you will not be able to recompile the source code. So you don't remember which version you used it for your applications. So that is in your old machine, but in your new machine, that is not available. Even you don't remember. That's really a problem. You want to recompile and want to run the program again, but that is not possible. So you keep them in your local project directory, then everything is there, that it is easy to recompile the source codes. And also you know the version of your software, which is easier to revise with the newer version of software. So my recommendation in this course is a local copy. So copy your library files to your project directory. So here we have hello, that is a project directory, and place your header file and lib file to your src directory, which is a source, and dll to your bin directory. So that is just installation. So because we use a pre-compiled libraries, so that is pretty easy to in this way. So this local copy is recommended because you don't have to worry about a compiler system where the libraries are not installed. Also, you can easily distribute your binaries in bin directory. Just copy your bin directory, that's it. Then you can run the program. So this is only for the Windows. When you use the Linux, then that is not easy in this way. So in case of Linux, just use the standard installation procedure, which is supported by some package manager. So when you use Windows, then follow this procedure. Then things to do in Visual Studio. So you have lib file. The header file is basically you can include it by the relative path to the header file, but lib file doesn't support relative path. So in the project option in Visual Studio, so right click for your project, and you see property here, and set the additional library in the linker option. So here your SRC directory gl/glfw is the location for your glfw lib file. Then now you are ready to link your library files. Okay, so far that was for the general usage of the third-party libraries, which are pre-compiled and distributed as a DLL and header and lib files. The next thing I'd like to explain is the VCPKG. So basically you can build libraries on your own from the original source. So you can download the source files from some GitHub or other similar repository, but it might be inconvenient, or often you have problems from the building on your own. So in that case, VCPKG is very useful. So now Visual Studio provides a good package manager that is a VCPKG. So that is similar to Scoop or Chocolately or sudo apt-get installed in Ubuntu. So that is a very similar interface for the download and install of the library.
So example here is the static build for x64. So now we like to install the GLFW3, probably latest version. Then you type in the command using vcpkg install and GLFW3 and x64 and Windows and static. So in that case, we can build libraries for the static linking. Also, we can install for the dynamic version almost the same. So in this case, GLAD x86 and Windows without static. So this means we can build dynamic libraries. So in this way, so we can simply build libraries, third-party libraries. Then so we may use directly for the Visual Studio, but still I recommend you copying the build to your local directories. And you can find the libraries so inside this directory, and you copy the files to your local project directory. Then you can you can use this the same way.
Next is we see the GL specific libraries. First, take a look at the architecture of the OpenGL software. So assume we develop in Windows, actually, except this one, and all the others are the same for like this way. That is the same for platform, different platforms. But WGL is a Windows GL library headers. That is for the platform specific features. So for Linux or other platforms, you have to use different libraries. But typically that is not directly handled by the user. GLFW uses the WGL internally. So you will not be able to see WGL in your application header. So this is your application program, and we're going to use three libraries: GLAD, GL, GLFW, and they are internally linked to WGL and graphics driver. GLAD will be shown. GLAD is an extension loader for OpenGL, and GL is the core of OpenGL, and GLFW is a OpenGL context and also some GUI and window creation. But we never install GL. Then when GL is installed, so that is actually easy. You install your graphics driver, then OpenGL driver is installed as well. So when you, in order to something on the screen, then you already have installed graphics driver. At that time, OpenGL is installed already. So we never install GL manually. Then that means we have to use third-party libraries of GLAD and also GLFW. So those two libraries are our third-party libraries that should be used for our samples. Then first see the OpenGL core. So OpenGL core library drivers. It's already installed on your compiler systems when you are installing display drivers for your operating system. So you need some header files that is installed with your development environment. So when you install Visual Studio, then OpenGL so actually the name is different. So GL's header file is installed as well. So implementations are available through graphics drivers. So we don't install them. Let me show where the OpenGL driver that is inside the Windows System 32. So in System 32, then you see OpenGL 32.dll. Yeah, it's only 1 megabyte. It's pretty small. This is actually the core of your driver. So that is actually when you installing your operating system, that is already there, but updated version is revised when you install your graphics driver. Then, so recent extensions are available through that driver file. So linking with Windows system, for Windows we need WGL, and also for Linux and we need GLX. For Apple we need AGL. So that is not handled by the user. That is usually provided by the windowing abstraction library such as the GLFW. To summarize, in your code, you don't need to do anything. So just do nothing for the OpenGL installation. So GLFW and GLAD CLAD do everything instead. So just include GLFW and CLAD will do everything you need for the OpenGL core. So next is a GLFW. So in this website, you're going to see GLFW. So GLFW is an open source and a multi-platform library. So you can easily download the GLFW in the website, or when using a package manager, then it can be downloaded easily using that package manager, such as sudo apt-get in the Ubuntu. So it's creating Windows with OpenGL context and receiving input and events. So you move your mouse or you press keyboard, then such events are transferred to this GLFW library. Then you can handle them using the callback function registered for the event types. GLFW is also written in C and has a native support for Windows OS X and many Unix-like systems using the X Windows system such as Linux or FreeBSD. So it is a modern alternative to old-school OpenGL utility toolkit GLUT. So it is much cleaner and also supports more platforms, and so some of the advanced features are available. So you can download the source code and build on your own, or there might be some pre-compiled distribution. So this course example will provide in-house pre-built binaries. So I compiled it on my own, and it is distributed as a part of your sample. Without this one, this sample file is not running. So this is not intended to distribute as a pre-compiled library. So don't distribute my DLL or lib file to other place that should be used only for this course. So in your code, so we need to do 3 things. So include glfw3.h and pragma comment lib glfw3.lib. This is equivalent to your setting this lib file into the project setting, but I prefer to use in this way. And also copy your DLL file to your program binary directory, which is a bin. This is only necessary when you are using DLL version. So in my sample, I provide 2 versions, static compiled version or DLL version. Okay, I think it's better to see how the code look like. So here are 2 directories inside your first sample. So glconf can be downloaded at the course website. So click the zip file in the course web page. Then you have these 2 directories. So inside the bin, then you have it inside SRC like this way. Then I show the header file here. So here we have to include glfw3.h. So in the SRC directory, you see so your solution project and the CPP file here, and in GL directory glfw, and here you have header file glfw3.h. So this is a lib file. I think this is a static library like that way. So lib file is there, and also your header file is there. And okay, that was the first step. Include your glfw3. Then here. Here's encode linking and Visual Studio. In the end, we're going to use this static library here, pragma comments here. So that is this one. So when we use a dynamic library, then we have to use this one. So it seems like a complex. So if defined MSC version, that means we are using the Visual Studio and its version is 1920. That is I think 2019. And if defined like this way, and so so IX86 is defined. That means we're using 32-bit, and X64 is defined and we are using 64-bit. If defined MSC version, that means we are using the older version of the Visual Studio. Then in that case we use the DLL version. Okay, then copy glfw3.dll when we are using the DLL version, but actually we are using static version now, so we don't have to copy this DLL file to the bin directory. So next is CLAD. CLAD is OpenGL extension loader generator library. So you can find it in this website. In this website, you can download the CLAD, and also you can generate the header file and C file from this website. So you configure your platforms that you can easily get its implementation, and you just include it in your source file, then that's it. So this makes it easy to access OpenGL extensions. So loading extension is a bit difficult, so you have to understand the explicit loading of the precompiled functions in DLL. So we don't do that, and also we have to know the function prototype. So all in all, they are quite complex, so this library handles everything you need. So all you have to do is just include the header file and C file in your project. So here we see clad.c here. This is generated by clad, something like that. And also you include clad.h. So first you have to include clad before the glfw. So we don't see the implementation, and just include header and clad.c in your project and your extension is ready. So in your code, clad.h and embed clad.c in your source project, then it will be compiled and its object file will be available for linking. Then you don't have problem. So if you don't embed clad.c in your project, then your compilation succeeds, but your linking will fail. So include clad.c. So that's it. And application needs only to run clad load.gl. Here we see clad load.gl here. At this point, we can load the OpenGL extensions. So that is also handled by the glfw, or we can directly load like this way. But when we are using glfw, it is better to use its own support for the clad. So that's it, very simple C library. So let me show some example from the web service of CLAD. So we can type the address here. So this is a really great website. So here we can generate the extension loader for many different versions of OpenGL and also different platforms. So in this website here, we use the C file, so which can be shared with the C++ and debug D. D is another language. For it, I have no idea. NIM is a recent language here, and also Pascal. The specification is OpenGL, and also we may generate EGL, GLX, WGL, but that is for the platform dependent some things, but we don't care about that. And here for the API, GLES and SC, I don't know what is that. And ES is a embedded system, and GL is definitely for the versions. Here we may use the latest version 4.6, but that is often not available. For safest option is just use version 3.3 and or that is a bit weird. So we can generate ES version and GL version together, but I think that is not a good idea. So use just GLES version 1, that's usually useless. So version 3.2 for GLES, and profile, always use a core profile. So because we use a modern style OpenGL, then I think that so we can select. This way. I think it's some better way, or add or. Then such extensions are specified in the source codes, and we press generate. Then we see that some temporary archive here. Then we can simply download it and include your source code. So that's it for the CLAD web service, and pretty easy. But in the course sample distribution, I already generated for our purpose, so you don't have to generate it again. But for another or additional development, you may generate on your own. Okay, next is how to configure OpenGL for Linux. So some of the students want to do that in Linux, then so I also provide some setup for the Linux, then that is also included in your sample distribution. So here you see makefile here. So this makefile is almost all in one makefile. So this makefile is the same for all of the sample projects. So you just make, and all of the sample will be built with this makefile. And this is also useful for Windows GCC and also Linux GCC. So when you do that in Linux, then you have to install the OpenGL library in Linux that is available as a Mesa. Mesa is an open source implementation of OpenGL, which is available in Linux. So first, install and update all the essential packages like this way. Sudo apt-get install build essential. Then all the GCC packages are installed in this way, and also do that update. And next is install the latest Mesa via PPA. So I don't explain what this means, but using this way or in this way, sudo add apt repository. So we add repository in this way, and apt-get dist upgrade and install mesa utils. In this way, we can install mesa. So there are alternative ways, but I don't explain here. You can easily find on the web. Next is installing glfw. So sudo apt-get install libglfw3 -dev. Then glfw is installed. So that is a basically global installation. So in Linux, that's not that easy to do that local installation. So in Linux, so I assume your program follows in this step and it should be compiled without problem. So once you're done with the installation, then you have to test your OpenGL works. So run this one glx info and grep version, then you can find the OpenGL version and run glx gears. Then you're going to see the screen like this way. Then your OpenGL works. So if you find version is OpenGL version is 1.4 or 1.3 something like that, then already no problem. So your OpenGL should support higher than 3. So in that case, troubleshoot like this way. So I don't provide full details of troubleshooting. Then you can find how to solve the problem in Linux for this one. So makefile. So most of the source files are distributed with makefile. So that makefile is the same file. So I wrote it to handle all of the cases. So you can simply copy the source code directories to your Linux environments and just simply run make. That's it. Then you're going to see it like this way. So that is for Linux, but still we can use GCC in Windows. So in Windows, there are two ways, like min-gw. That is a Windows compatible distribution of GCC. So using min-gw, we can still use the GCC and makefile, and also we can develop OpenGL program, or we can use WSL Windows subsystem for Linux. So in this way, we can install the Ubuntu inside our Windows. Then we can run the native Linux. So there are more details on the web. If you want to use WSL, then try to find the details of how to install the WSL and also some other necessary steps. Then next is putting it all together. So we run, we bring it all together in our first sample program, cgconf. So hello OpenGL. So this is the source code. There might be a slight change in real distribution, but here is you can catch the idea. So GL, so we first include glad.h and glfw3.h. And here's the main functions and printf hello OpenGL. And first do initialization from glfw. It should succeed. I have never seen this fails, but I guess yeah, other cases it will succeed. And we set some hints for the window creations. Visible false. Context version 3. Minor version 3. So our OpenGL should support 3.3. That is a minimum requirement for our OpenGL programming. And also, OpenGL forward compatibility profile is set to true. So we only use a forward compatibility. We don't use a backward compatibility. So OpenGL profile is a core profile. So this is a very good starting point, and don't use some out of date legacy profile and also functions. So your core profile doesn't support something, then don't do that. So that is a good practice in your modern OpenGL programming. Then next is create window, GLFW create window. This is window size but no meaning because we don't show window here. And this is the title and this is optional, so we don't provide. Then window will be created. Then next we do GLFW make context current. So always your window is associated with a context that you have to say we're going to use that context for our OpenGL. That is done by this function. Then your OpenGL is now ready to use. And then so actually at this point only OpenGL 1 point something is available. That is not enough. For the later recent extensions are available through extension. So we load them using this glad load GL. Then all the extensions higher than 1 point something functions are available through glad load GL. Then now we test our OpenGL version like that. You are using something like that. OpenGL shading language version, GPU, and vendor. Then we run the program. Then here, hello OpenGL, you are using OpenGL 3.3 when this is driver version and shading language version 3.3. And also GPU is a GTX GeForce RTX 3090 and vendor is NVIDIA. So you have to see like that one, then OpenGL version should be higher than